we are not yet done. There are more strange territories to walk through before sleep finds you. Let us talk for a moment about black holes, because they deserve more than passing mention. They are not simply the final remnants of the universe. They are among the strangest objects that physics has yet been forced to accept, and they have a quality that is almost philosophical in its implications. A black hole forms when matter collapses under its own gravity to such density that even light cannot escape. The boundary beyond which escape is impossible is called the event horizon, and it is not a physical surface. It is a region of space-time, not a wall, but a threshold, beyond which the geometry of space and time is so warped that all possible futures lead inward, toward the singularity at the center. There is no way out, not because of a barrier, but because there is no direction in which out exists. Inside the event horizon, toward the singularity, is not a direction in space. It is the direction of time. This is one of the most unsettling ideas in all of physics. Inside a black hole, the future is a place, not a time. The singularity is not where you will be eventually. It is when you will be. You cannot avoid it for the same reason you cannot avoid next Tuesday. All of this makes the event horizon not just a physical boundary, but something approaching a philosophical boundary. A place where the ordinary meanings of the words before and after begin to dissolve. And yet, thanks to Hawking, they are not eternal. They radiate their mass away into the void on timescales that make the current age of the universe seem like the first heartbeat of an infant. But they do it. They do dissolve. They do eventually return everything they have swallowed to the universe at large. This is itself a source of deep uncertainty in physics. The question of what happens to the information contained in matter that falls into a black hole, the exact quantum state of every particle that ever crossed the horizon, is one of the deepest unsolved problems in theoretical physics. The information paradox, as it is called, asks whether black hole evaporation is a process that preserves information or destroys it, and the answer matters enormously because the laws of quantum mechanics hold that information can never truly be destroyed, only transformed. Whether Hawking radiation carries the encoded information of everything the black hole ever swallowed, scramble beyond any practical recovery, but in principle retrievable, or whether information is simply annihilated when a black hole evaporates, is a question that the greatest minds in physics are still debating with genuine, unresolved passion. There is something almost tender about this debate. In the face of a universe headed toward absolute disorder, physics insists that information is sacred, that everything that ever happened in principle leaves a permanent mark on the fabric of reality. The universe, even as it forgets itself, keeps a record. The cosmologist Lee Smolin has proposed something even stranger, something that lives at the boundary between science and poetry, the idea of cosmological natural selection, which suggests that black holes give birth to new universes, each with slightly different physical constants, and that the universes best suited to producing black holes, which means the universes with the physical constants most conducive to the formation of complex structures like stars and galaxies and planets and life, are the ones that reproduce most prolifically in a cosmic analogue of Darwinian selection. This is not a mainstream view, but it is not outside the bounds of serious speculation. and it offers a picture of the cosmos as not a single story, but an ecosystem of stories, branching and branching in the dark, each new universe a child of the collapse of a star, carrying the inheritance of its parent and the possibility of something new. Even if this is not literally true, and we do not know whether it is, it points toward something that feels important. The universe, as far as we can tell, it tends toward complexity before it tends toward simplicity. The road from the Big Bang to the heat death is not straight. It loops and doubles back and climbs. It produces, along the way, things that are their own reward, not because they were intended, but because the physics permits them. Because in the vast, cold, expanding dark, the conditions were briefly, locally, exquisitely right. You are one of those conditions. This is not metaphor, it is physics. Sleep, if it is coming for you now, let it come. You do not have to hold all of this. You do not have to resolve it or file it away or reach a conclusion. The universe has had 14 billion years of questions and has not finished answering them. You are allowed to simply rest in the not knowing, in the vast, dark, star-scattered space of it, and let your breathing slow. But if you are still with me, let us go a little further, because there is something I want to tell you about rebirth. The heat death, if it comes, is not the annihilation of everything. It is the annihilation of usable difference. The energy still exists. The photons still exist, spread thin as whispers through an infinite dark. The mathematics that describes them has not stopped being true. The laws of physics, the deep regularities in the behavior of reality, are not destroyed by entropy. They persist. They are, in some sense, more fundamental than the matter and energy that obey them. And there are physicists and cosmologists who have speculated seriously and carefully that from the heat death, under exactly the right quantum fluctuations, a new low entropy state could arise, a new singularity, a new Big Bang, not because of any mystical necessity, simply because quantum mechanics allows for it, because in a universe that lasts long enough, even the most improbable events are not just possible but inevitable. The physicist Roger Penrose has proposed a model he calls conformal cyclic cosmology, in which the universe, at its most extreme dilution in the far future, when all massive particles have decayed or fallen into black holes and only massless photons remain, becomes mathematically indistinguishable from a new Big Bang. The conformal structure of space-time, the geometric patterns that remain when all scales are stripped away, allows the cold, empty end of one universe to match seamlessly onto the hot, dense beginning of another. In this view, the Big Bang was not a beginning. It was a continuation, and our universe is not the first. It is one in a sequence that may be infinite in both directions. Cycles within cycles. Death within rebirth within death. The void that breathes. The silence that remembers how to speak. We do not know if this is true. We may never know, but we can hold it alongside the heat death, as one hand holds a cold stone and the other holds a warm one, and feel the contrast, and notice that neither cancels the other out. The universe may end in cold silence, and from that silence may come something new that we cannot name or imagine. Or it may simply end in the fullest and most final sense. Either way, what we have had is real. The warmth was real. The light was real. The 14 billion years of stars were real. The 4 billion years of life on this unremarkable planet were real. You are real. this moment is real. And the fact that it will end eventually in one way or another does not make it less real. In some strange way, it makes it more. The Buddhist traditions have known this for millennia, though they arrived at it through contemplation rather than cosmology. Impermanence is not the enemy of value. It is the condition of value. A song is not less beautiful because it ends. A fire is not less warm because it burns out. A star is not less magnificent because it will one day become a white dwarf and cool in the dark for 1,000 trillion years. The ending is part of the form. The decay is part of the beauty. And entropy, the great dissolver, the slow and patient enemy of every structure you have ever loved, is also the very thing that makes structure possible. Without the arrow of time, without the asymmetry between past and future, without the flow from lower entropy to higher, there would be no change, no process, no causation, no story, no you. Entropy is why you exist, and entropy will in the end return everything you are made of to the soft anonymity of the void. But between now and then, here is this. Here is the warmth. Here is the particular and improbable configuration of atoms that wonders about its own ending. Here is the consciousness that can look out at the size of the universe and feel something. Not just record it. Feel it. I wonder sometimes, in the hours that belong to this kind of thinking, whether the ability to feel the grief of endings is not a flaw in the design, but the most sophisticated thing the universe has yet managed to produce. The universe cannot mourn itself, but you can. You can hold the fact of your own ending, and the ending of the ones you love, and the ending of the sun and the stars, and the eventual dissolution of every particle that has ever composed anything, and feel something about it. That is not a small thing. That is the universe looking at itself through eyes that know they are temporary, and choosing, for the duration of their time, to see. We are near the end of our journey tonight, and I want to bring you back, slowly, from the vast cold distances we have been traveling, back toward the warmth of where you are, back toward the slow rhythm of your own breathing, back toward the particular and unrepeatable fact of you here now. The universe will die. Not soon. Not in any sense that matters to you or to anyone you will ever love. The stars will burn for trillions of years. The black holes will hold their mass for googles of years. The photons of Hawking radiation will drift through an empty cosmos for timescales that no word in any language is adequate to name. And somewhere in all of that time, somewhere in the long arc from the first hot, dense beginning to the last cold, thin ending, there was this. There was you. There was the weight of a blanket. There was the particular smell of the room you are in. There was the sound of your own heartbeat if you are quiet enough to hear it. There was the question of what your life means, asked softly in the dark to no one and everyone. These are not small things. These are the universe being complex. These are entropy on its way to maximum, pausing to notice itself. These are the 14 billion year project of existence, arriving for a moment at the strange capability of self-reflection. You are what the universe looks like when it becomes curious about itself. You are what matter does when it has been organized long enough and intricately enough to ask questions. And tonight, those questions can rest. Tonight, the atoms can stop trying to understand their own eventual dissolution and simply be what they are: warm, arranged, breathing, alive. The void will wait. The entropy will wait. The heat death is patient beyond all patience, and it does not need your worry. It will arrive, or something will arrive, in its own time and in its own way. And none of it requires your vigilance tonight. Let the thought of the stars dissolve behind your eyelids like the stars themselves, slowly, over unimaginable time. Let the image of the last black hole fading to nothing give you permission to let go of the smaller things you have been holding today. Let the silence of the heat death be, for now, simply a silence. Let it be a permission to be still. The universe was 17 billion years in the making before it made you. It will last, in one form or another, for incomprehensible trillions of years beyond you. But right now, in this particular and unrepeatable arrangement of its atoms, it is resting. You are resting. The questions are still. The entropy is still increasing, quietly, in the dark, as it always does, as it will always do. But you do not have to watch it. You do not have to help it along. Just breathe. Just be. Just let the darkness be warm and the silence be kind. Before I leave you to your sleep, I have one last question, and I want you to take your time with it. We have traveled together tonight from the beginning of time to its end. We have passed through stars and black holes and the vast cold silence of a heat-dead cosmos. We have looked at entropy and found in it somehow a strange beauty. And I want to know, in the face of all of that, in the face of the sheer scale of what we are part of, do you feel small or do you feel vast? Do you feel like a speck of dust caught in an indifferent machine? Or do you feel like the most extraordinary thing the universe has managed to produce so far? There is no wrong answer, but I genuinely want to know yours. Write it in the comments, even in the middle of the night, especially in the middle of the night, because these are the hours when the honest answers come. Sleep now. The stars are still burning. The universe is still enormous. The entropy is still climbing. And you, in the middle of all of it, are exactly where you are supposed to be. Resting, warm, temporary, and for this moment, perfectly here. Good night, and thank you for traveling with me into the infinite loop. But wait. Stay a little longer. There is more to say, and the night is long, and we are only beginning to understand the depth of what we have touched. Let us return to entropy, because I do not think we have fully honored it yet. We have spoken of it as a law, as a direction, as the arrow of time. But entropy is also a kind of language. It is the language the universe speaks when it is explaining what is real, what is possible, what is gone, and what is not yet. Every single process you have ever observed, every single experience you have ever had, every single moment that has ever felt irreversible, the way a word once spoken cannot be unspoken, the way a year gone by cannot be relived, the way the dead do not return. All of this is entropy speaking. All of this is the universe narrating itself in the only direction it knows how to move. The mathematician and physicist Ludwig Boltzmann, who gave us the mathematical framework for entropy in the 19th century, spent much of his life trying to derive the directionality of time from the underlying time-symmetric laws of mechanics. His work was brilliant and visionary and deeply misunderstood in his lifetime. He died by his own hand in 1906 while on holiday in the village of Duino near Trieste. He was 62 years old. The irony which is the kind of irony only the universe can produce without intending to, is that within a few years of his death, his ideas were vindicated absolutely. The statistical mechanics he developed became one of the foundational pillars of modern physics. His gravestone in Vienna bears his famous equation, the relationship between entropy and the number of microscopic configurations available to a system, an equation of such elegant simplicity that it seems impossible it could contain so much of what we know about time and change and irreversibility. Boltzmann understood something that most people still do not fully appreciate. Entropy is not a property of matter, the way mass or charge is a property of matter. It is a property of our description of matter. It depends on what we choose to count as the same and what we choose to count as different. A room full of gas, spread uniformly in all directions, has higher entropy than the same gas compressed into one corner, not because of any intrinsic quality of the atoms themselves, but because there are vastly more ways to arrange atoms uniformly than to arrange them all in one corner. The second law of thermodynamics is, at its heart, a statement about probability. High entropy states are common, low entropy states are rare, and rare states left to themselves tend to become common states, not because of any force pushing them, simply because there are more ways to be common than to be rare. The universe is not moving away from order. It is moving toward the most probable arrangement of its ingredients. And the most probable arrangement of its ingredients is, in the long run, a uniform and undifferentiated warmth, and then a uniform and undifferentiated cold. This is humbling. This is one of the most humbling ideas in science. The arrow of time, the fact that we can remember the past but not the future, the fact that causes precede their effects, the fact that broken things do not spontaneously mend. All of this emerges not from any fundamental law that distinguishes past from future, but from the contingent fact that the universe happened to start in an extraordinarily low entropy state. The Big Bang was not just the beginning of time and matter and energy. It was the beginning of the vast improbability that has been slowly, incrementally, exquisitely becoming probable ever since. We live in the middle of a cosmic slide from one of the rarest configurations that matter can occupy to one of the most common. And everything that feels precious, everything that feels irreversible, everything that feels like the weight of real experience arises from that slide. The philosopher Hugh Price has argued that the real mystery of the second law of thermodynamics is not why entropy increases toward the future. That is easy to understand statistically. The real mystery is why entropy was so low in the past. Why did the universe begin in such an unlikely state? This is a question that points all the way back to the Big Bang, to the initial conditions of the cosmos, and from there to questions about why there is something rather than nothing, why the laws of physics have the particular form they have, why the constants of nature are tuned to values that allow complexity to exist at all. These are questions for which we do not have answers. They may be questions for which we can never have answers, not because we are not clever enough, but because the answers may lie outside the causal structure that our own existence depends on. You cannot see the edge of the frame from inside the picture. You cannot explain the initial conditions of your universe by appealing to processes that required those initial conditions to already exist. And yet, we keep asking. We keep building telescopes and particle accelerators and mathematical frameworks of extraordinary abstraction. We keep sending our minds out into the dark, past the stars and the galaxies and the edge of the observable universe, asking, what is this? What does it mean? Is there a reason? And sometimes, in the asking, we feel something that might be called awe, and might be called grief, and might be called love, because all of these feelings arise from the same source, the recognition of something so much larger than ourselves that we cannot contain it, and the strange fact that we are part of it anyway. You are part of it. The carbon in your body was made in the nuclear furnace of stars that died billions of years before you were born. The iron in your blood was forged in supernova explosions of such violence that for a few weeks they outshone entire galaxies. The hydrogen that makes up most of the water in your body is as old as the universe itself, older than the first stars, older than the first galaxies, primordial and patient and indifferent, and somehow, after 14 billion years of being shuffled around, arranged into something that can lie awake in the dark and feel the weight of the cosmos pressing gently down. The astrophysicist Neil deGrasse Tyson has said, and I am paraphrasing because the beauty of it deserves its own phrasing here, that we are not in the universe. We are of it. We are one way the universe has organized itself to know itself. And that knowing, that capacity for wonder and for grief, and for the specific and peculiar feeling of lying awake at night, wondering whether any of it means anything, is not incidental to the universe's story. It is, as best we can tell from inside the picture, one of the more interesting things the universe has managed to do with its 14 billion years. Let me tell you something about light. Not just light as illumination, but light as information. Light as the fundamental currency of the cosmos. When you look up at a clear night sky, every star you see is a message from the past. The light from the nearest star, beyond our own sun, Proxima Centauri, takes approximately 4 years to reach us. The light from the stars in the Orion Nebula, that soft blur visible to the naked eye in winter skies, took approximately 1,300 years to arrive. The light from the Andromeda Galaxy, that faint smear of light visible on a dark night, 2.5 million years. When you look at the night sky, you are looking at multiple different pasts simultaneously. The sky is a palimpsest, a document written over itself again and again by different ages of the universe, all arriving at your eye at once. And here is the strange consequence of the universe's accelerating expansion. Every year that passes, more and more of those lights go dark. Not because the stars themselves have died, but because the light they are currently emitting will never reach us. The expansion of space is carrying those sources away from us faster than their light can travel toward us. We live in an island of visibility that is slowly, inexorably shrinking. In 1 trillion years or so, the sky of whatever observing entity might exist would be nearly empty of galaxies. Only the merged remnants of our own local group would remain visible. Everything else would be gone, as cleanly and completely as if it had never been. The universe would have contracted in observable terms from 2 trillion galaxies to a single small cluster. all that richness swallowed by expansion, all that information locked forever beyond the horizon. This is a kind of death, too, not of the galaxies themselves, which continue to exist and evolve beyond the horizon, indifferent to our inability to see them, but of the relationship, of the possibility of connection, of the chance that something in one of those galaxies might reach towards something in ours and find a way to bridge the gap. The loneliness of the very long future is not the loneliness of being the last remaining thing. It is the loneliness of being one of many remaining things and being separated from all the others by a distance that no signal, no force, no intelligence could ever cross. We have not talked enough about the quantum world, and I want to spend a few quiet minutes there, because the quantum world is where our story gets genuinely strange in ways that no metaphor quite captures. And yet it is also, in its strangeness, oddly comforting. Quantum mechanics is the physics of the very small, and it is the most precisely tested theory in the history of science. Its predictions have been confirmed to accuracies of more than 10 decimal places. It is not speculative. It is not approximate. It is the most successful description of physical reality that human beings have ever constructed. And one of its central features is that reality at the quantum level is fundamentally probabilistic, not just in practice, because we lack the information to predict precisely, but in principle. The world is not determined in advance. A radioactive atom does not have a hidden clock that will go off at a specific time. Its decay is genuinely random, with a probability distribution in time, but no fixed moment. An electron approaching a detector does not have a definite position before it is measured. It exists in the superposition of all possible positions, described by a wave function, until the moment of measurement, at which point the wave function collapses to one definite outcome. But there was no fact of the matter about which outcome it would be before the measurement occurred. This randomness is not a bug. It is arguably the most important feature of the quantum world for the long-term story of the universe, because it means that the future is not written, not in any microscopic detail. The second law of thermodynamics tells us the broad direction of travel, toward higher entropy, toward equilibrium. But the specific path, the particular configurations of atoms and fields along the way, the exact sequence of events between now and the heat death is not determined. It is built, moment by moment, out of an immense number of probabilistic quantum events, each one genuinely undetermined until it occurs. This means, among other things, that the universe is not a machine running a pre-written program. It is, in some sense, improvising. The overall direction is set by thermodynamics. The details are negotiated at every instant by the probabilistic dance of quantum reality. And somewhere in that space between the determined direction and the undetermined details, there is room for the extraordinary, room for the improbable, room for the specific, unrepeatable, improbable configuration of atoms that is you, lying in the dark tonight, wondering about the end of everything. Probability is not destiny. A high-entropy future is probable. You are improbable. Both of these can be true simultaneously. And the improbable, given enough time and enough possibilities, does not just happen. It happens repeatedly. It happens in different forms. It happens in ways we cannot anticipate. The universe has already surprised us more times than we can count. The fact that it started from a nearly featureless hot plasma and produced, in 14 billion years, atoms and molecules and galaxies and stars and cells and nervous systems and consciousness and music and the specific form of grief that comes from understanding your own impermanence. None of this was predictable from first principles. All of it arose from the probabilistic landscape of quantum possibility unfolding within the thermodynamic constraints of an expanding universe. What comes next, over the long ages between now and the heat death, is not fully predictable either. The most we can say is that entropy will increase, that stars will burn out, that black holes will form and evaporate, and that eventually, on timescales beyond imagination, the universe will reach a state of maximum entropy and minimum complexity. But whether that state is truly final, whether it is the last page of a single story or the closing of one chapter in a larger cycle, whether the quantum fluctuations of an empty universe might eventually seed something new, we do not know. The mathematics does not give us certainty, only probability. And probability, in a universe with enough time, leaves room for almost anything. I find that genuinely comforting. I do not know why exactly. Perhaps because it means that the future, however cold and dark and entropic it may eventually become, has not been finalized. Perhaps because it means that the story we are in is not pre-written. Perhaps simply because uncertainty, which can feel so frightening in the daylight hours, has a different quality in the dark, when the stars are out and the scale of things has expanded past the point where our ordinary anxieties can reach. Uncertainty at this scale is another name for openness, another name for the not yet determined, another name for possibility. And possibility is what the universe has always been about. From the first fraction of a second after the Big Bang, when the primordial plasma of quarks and gluons was cooling rapidly and the fundamental forces were separating from their initial unified state, to the slow cooling of the last white dwarfs trillions of years from now, the universe has been a space in which possibility unfolds. Some of it unfolds into catastrophe. Some of it unfolds into beauty. A great deal of it unfolds into things that are neither beautiful nor catastrophic, just quietly happening. Protons fusing in stellar cores, hydrogen clouds slowly condensing under gravity, atoms bonding and unbonding in the chemistry of interstellar space. But some of it, some tiny and improbable fraction, unfolds into the extraordinary, into life, into awareness, into the capacity to ask what this all means and to feel something about the answer. You are that fraction. You are the universe's brief, improbable, extraordinary experiment in self-awareness. And tonight, this experiment is resting. Tonight, the atoms are taking a break from wondering. Tonight, the question can simply be released into the dark, like a leaf falling into still water, spreading its rings, and then going quiet. The heat death will come. Not soon. Not in any sense that touches the life you are living or the lives of anyone you will ever know. But it will come. And between now and then, there is this, the warmth of the present moment, the particular and unrepeatable feeling of being alive on a small planet orbiting an unremarkable star in the outer reaches of a spiral galaxy in an observable universe, 14 billion light-years across, surrounded by approximately 2 trillion other galaxies, each containing hundreds of billions of stars. In a cosmos so vast that the number of atoms in the observable universe is approximately 10 to the power of 80. And yet, in all of that immensity, here you are, specific and warm and wondering. That is not nothing. That is, in a very real sense, everything. Everything the universe has produced so far, everything it has burned and built and dissolved and rearranged over 14 billion years, has been, whether it knew it or not, working toward this moment of self-recognition, of temporary, fragile, magnificent awareness, of you. Sleep now. Let the stars burn. Let the black holes hold their silence. Let the entropy climb its slow and patient ladder. Let the universe do what it does. Expand and cool and complicate and simplify and expand again and cool again. You do not have to help it. You do not have to watch it. You have done your part today simply by being, simply by thinking, simply by feeling the weight of it all and choosing to rest. The void is patient. The heat death is far away. The silence at the end of time is waiting. But it is in no hurry. And between now and then, here is the warmth. Here is the dark. Here is the soft machinery of your own breathing, steady and slow and beautiful. A tiny local pocket of order in a universe that is slowly, gently, inexorably becoming disorder. Let it be enough. Tonight, let it be enough. The last black hole will fade in a Google of years. The photons of its radiation will drift in the cold for longer still. And somewhere in the deep mathematics of what comes after, in the probabilistic quantum landscape of an exhausted cosmos, there may be the seeds of something new. Or there may be simply the silence. Either way, the story you are living right now is not diminished by its ending. It is defined by it, sharpened by it, made more vivid and more precious by the fact that it is happening at all, against all odds, in the middle of a universe that had absolutely no reason to produce you. And yet, here you are, breathing, thinking, wondering, letting go. Good night. You are made of stars. You will return to stars. And in the long middle, which is what we call a life, you are this. Warm, temporary, improbable, and real. Welcome always to the cosmos and dust. Imagine a moment so far in the future that every single word in every single language ever spoken on this earth would not be enough to count the years between now and then. Imagine a silence so absolute that even the concept of sound has forgotten it ever existed. Imagine a darkness not made of night, but made of the absence of everything that ever burned, or glowed, or pulsed, or breathed. That moment is coming. It has always been coming. And the strangest, most quietly devastating truth in all of science is this: the universe has known it from the very beginning. Welcome to the cosmos and dust. If you are here in this moment, wherever you are in the world, lying in the dark, with your thoughts slowly beginning to soften at their edges, then you are exactly where you are supposed to be. Subscribe if this is your first time joining us, and settle in. Let your shoulders drop. Let your jaw unclench. Let the weight of the day begin to dissolve, because what we are about to explore together is so vast, so ancient, so quietly magnificent, that your own worries, as real and heavy as they feel right now, will seem for a little while like specks of dust caught in an afternoon light, which, in a very literal and scientific sense, is precisely what they are. Close your eyes if you wish, or let them rest unfocused on the ceiling or the dark above you. We are going somewhere that takes no effort to reach because it is everywhere. It is woven into the fabric of every atom in your body and every breath you draw. We are going to the end of everything, and we are going to find in that ending something unexpectedly tender. Let us begin at the beginning, because to understand the death of the universe, we must first understand what it means to be alive. Not alive in the biological sense, though that is part of it. Alive in the cosmic sense, pulsing, burning, ordered, complex. The universe, as it stands today, approximately 14 billion years after the event we call the Big Bang, is a place of extraordinary, almost absurd richness. There are stars being born in vast clouds of hydrogen and helium as you breathe right now. There are planets forming from rings of dust and ice around distant suns whose light will not reach us for thousands of years. There are galaxies colliding in slow, magnificent catastrophe. There are hundreds of billions of stars passing through each other almost entirely without touching, because the distances between stars within a galaxy are so immense that two galaxies can merge like two ghosts walking through each other, barely disturbing a single solar system. And there is life. Here, at least, on this small and improbable rock, spiraling around an unremarkable yellow star on the outer edge of a middling spiral galaxy in what cosmologists have come to call the local group, there is life. There is you. There is the sound of your own breathing. There is the warmth of whatever covers you. These are not small things. These are, in the context of what we are about to explore, extraordinary things. Miracles of temporary order in a universe that has been, since its very first fraction of a second, engaged in the slow and patient work of becoming disorder. This is where entropy enters our story, and entropy is perhaps the most quietly devastating idea in all of physics. The second law of thermodynamics, stated plainly, says that in any closed system, entropy, which is to say disorder, which is to say the number of ways a system can be arranged, will tend to increase over time. Heat flows from hot things to cold things. Never the reverse, not spontaneously. Ice melts in a warm room. It does not reassemble from the puddle on its own. Smoke spreads through a room. It does not gather itself back into the shape of a fire. A glass falls from a table and shatters. The shards do not leap upward and reconstitute the glass. These are not merely practical observations. They are reflections of something fundamental and irreversible about the nature of time itself. The physicist Arthur Eddington once said that entropy is time's arrow. It is the only law in physics that distinguishes between the past and the future. Every other fundamental equation, the laws of motion, gravity, electromagnetism, even most of quantum mechanics, works equally well in both directions of time. Run the film backward and the physics still holds. But entropy does not. You can tell at a glance whether a film of a breaking glass is being played forward or backward. Entropy is the reason. Entropy is how we know which direction time is flowing. And entropy, applied to the universe as a whole, is the mechanism by which everything that exists will eventually cease to be anything other than a uniform, cold, featureless void. That void has a name. Physicists call it the heat death of the universe. And it is the most probable, the most scientifically well supported, the most deeply strange fate that cosmology has yet imagined for the cosmos we inhabit. To understand how it will unfold, we need to travel forward in time, not by years, not by thousands of years, not even by millions. We need to travel by scales so large they defy ordinary imagination, and the only tools we have are mathematics and metaphor and the willingness to let the mind go soft and open, like a hand unclenching in sleep. We are now. We are 14 billion years after the Big Bang. The universe is still young in a certain sense. It is middle-aged, perhaps. The stars are still burning. There are still vast reservoirs of hydrogen available as fuel. The stelliferous era, the age of stars, has billions of years yet to run. Our own sun, formed roughly 4.5 billion years ago, has perhaps another 5 billion years before it exhausts the hydrogen in its core and begins to die. When it does, it will do what all stars of its mass do. It will swell into a red giant, its outer layers expanding outward until they engulf the inner planets. Mercury first, then Venus, possibly Earth. The oceans will have boiled away long before that, in perhaps 1 billion years from now, as the sun slowly brightens and the surface temperature of the Earth creeps upward past the threshold where liquid water can exist. Life, if life is still here, will have long since adapted or migrated or ended. The red giant phase will last for hundreds of millions of years, and then the outer layers will drift away in a haze of gas and dust, what astronomers call a planetary nebula, a luminous shroud slowly dissipating into the interstellar medium. What remains at the core will be a white dwarf, a sphere roughly the size of the Earth, but containing roughly the mass of the Sun, made of carbon and oxygen, no longer fusing, merely radiating away the heat it accumulated over billions of years of nuclear burning. A white dwarf cools. This is a process of almost incomprehensible slowness. The estimated time for a white dwarf to cool to temperatures close to the cosmic background, to become what is sometimes called a black dwarf, a cold, dark, inert remnant of a star, is on the order of 1 quadrillion years. That is a number so large that compared to it, the current age of the universe is less than a rounding error. It is, to put it in words, 1,000 trillion years, and by that measure our sun is a newborn, barely out of the cosmic womb. But here is the first of many strange reversals in this story. The universe may not live long enough to produce a single black dwarf, because something is happening to the universe that was not expected, not predicted, not understood even in principle until the closing years of the 20th century, and it changes everything. The universe is not just expanding, it is accelerating. In 1998, 2 teams of astronomers studying the light from distant supernovae made a discovery so unexpected that it earned its discoverers the Nobel Prize in Physics and overturned nearly everything cosmologists thought they understood about the long-term fate of the cosmos. The universe is not slowing down under the influence of gravity as most models had predicted it would. It is speeding up. Galaxies are not just moving apart. They are moving apart faster and faster with each passing moment. Something is driving this acceleration, something that has been given the name dark energy, a phrase that communicates both how little we understand it and how fundamental it must be, since it appears to constitute approximately 68% of everything in the universe. What this means for the long-term future of the cosmos is profound and, in its own way, beautiful. Because of dark energy, the universe will expand forever. And as it expands, the distances between galaxies will grow until the light from those galaxies, traveling toward us at the fastest speed anything can travel, will never reach us. They will be carried away from us faster than light can bridge the growing gap. One by one, over trillions of years, the galaxies will wink out of our observable sky, not because they have gone dark, but because they have passed beyond the cosmic horizon into a region of space-time that is forever unreachable and unknowable. This is a loneliness on a scale that staggers language. The Milky Way and its nearest large neighbor, the Andromeda Galaxy, will merge in roughly 4 to 5 billion years in that slow-motion gravitational ballet of two galaxies intertwining. The result will be a single larger galaxy, sometimes called Milkomeda in the popular imagination, a great elliptical cloud of stars. And over the following hundreds of billions of years, the other members of our local group of galaxies will also fall together under gravity, merging into a single vast remnant. But every other galaxy cluster, every other congregation of stars in the observable universe will retreat beyond the horizon, taking their light with them, taking their possibility with them. In a universe of perhaps 2 trillion galaxies, only one gravitationally bound structure will remain visible from any given point in the cosmos. Everything else will have been swallowed by the expansion of space itself, as completely and finally as if it had never existed. And yet, in a sense, those galaxies will still be out there, still burning for a while, still full of stars and the possibility of worlds, just forever unreachable, like a memory of warmth in a cold room. Pause here for a moment in the slow drift of this thought. There is something in this image of islands of light separated by ever-growing oceans of dark that feels strangely personal, does it not? The universe, in its expansion, is engaged in a kind of forgetting, a slow letting go. And perhaps you know something about that. The things and people and moments that once seemed permanent, that once seemed close enough to touch, that drift further away over time until they exist only as light you can still see but can no longer reach. If this speaks to something in you, I want to hear it. What is it that you are letting go of, or struggling to let go of, or maybe just beginning to make your peace with? Write it in the comments below. Not because I can answer, but because sometimes the act of putting a feeling into words, even small words, even in the middle of the night, is its own kind of astronomy. A way of saying, I was here, I felt this, I looked up. We continue. The stars are still burning in our distant future, Milkomeda. But they are burning through a finite supply of hydrogen. The universe is not making new hydrogen, not in any significant quantity. What exists now is all there is and all there will ever be, and the stars are consuming it. Slowly, patiently, over trillions of years, but consuming it nonetheless. The most massive stars, the blue supergiants that burn so furiously they exhaust their fuel in mere millions of years, will already be gone. What remain after many trillions of years will be the small stars, the red dwarfs, dim and cool and patient, burning their hydrogen so slowly that a single red dwarf can live for 10 trillion years or more, longer than the current age of the universe by a factor of nearly 1,000. 10 trillion years from now, the sky as seen from any surviving world would be strange and dim and rust-colored, lit by the faint glow of red dwarf stars that have barely changed since the universe was young. Life, if it exists, would need to be extraordinarily patient and extraordinarily adapted to the cold. But 10 trillion years is still not the end. It is barely the beginning of what comes next. As the red dwarfs burn their last hydrogen and cool into darkness, the universe will enter what cosmologists call the degenerate era. This is a universe made almost entirely of compact remnants. White dwarfs slowly cooling, neutron stars spinning in the dark, black holes, silent and massive and patient. The temperature of the universe will have fallen to fractions of a degree above absolute zero, that lower limit of temperature at which thermal motion ceases, and atoms, if there are still atoms, barely vibrate at all. There will be no new stars forming because there is no gas left to form them. The stellar nurseries will have closed their doors. And yet, the universe will not be entirely dead. Not yet. Because there are processes that operate on timescales so vast that they seem impossible. Processes that are not just slow, but almost unimaginably slow. And they will still be occurring in the dark, in the cold, in the patient void. One of these processes is proton decay. The proton is the particle at the heart of every atomic nucleus. It is, as far as we can directly observe, stable. A proton in isolation, as far as experiment has been able to determine, has not been seen to decay in the lifetime of the universe. But many theories in physics, particularly those that attempt to unify the fundamental forces, predict that protons are not truly stable, that they will eventually decay into lighter particles and radiation. The predicted half-life of a proton, depending on the theoretical model, is somewhere between 10 to the power of 33 years and 10 to the power of 45 years. To put the smaller of those numbers in words, it is 1 followed by 33 zeros. 1 decillion years. If proton decay occurs, then over timescales of this order, every atom in every white dwarf and neutron star and cold rocky planet will eventually come apart, dissolving into electrons and positrons and neutrinos and photons of radiation, until nothing made of ordinary matter remains in the universe at all. What remains after proton decay has run its course is a universe of black holes scattered across an immense, cold, dark, almost perfectly empty space, each one sitting in silence, each one a monument to the mass that once burned in stars or rested in the hearts of galaxies, compressed now to a point of infinite density behind an event horizon from which nothing escapes. Or so it was thought. In 1974, the physicist Stephen Hawking published a calculation that changed the story entirely. Using a combination of quantum mechanics and general relativity, Hawking showed that black holes are not truly eternal. They radiate slowly, imperceptibly slowly. But they radiate. The mechanism involves quantum uncertainty, specifically the phenomenon by which pairs of virtual particles spontaneously appear at the edge of a black hole's event horizon. Normally, a particle and its antiparticle would annihilate each other immediately. But at the horizon, one particle can fall inward while the other escapes outward as real radiation. From the outside, this looks as if the black hole is glowing very faintly, with a temperature that depends inversely on the black hole's mass. The more massive the black hole, the colder it glows. The supermassive black hole at the center of our galaxy, weighing several million times the mass of our Sun, glows at a temperature of approximately 1/10,000,000th of a degree above absolute zero. That is not a temperature you can measure with any instrument that exists or is likely to exist. But Hawking radiation is not nothing. It is real, and it means that black holes are losing mass. Slowly, so slowly, but losing it nonetheless. And as they lose mass, they get hotter. And as they get hotter, they radiate more intensely. And toward the very end of a black hole's life, in its final moments, in cosmic terms, the radiation becomes an actual burst of energy. A flash, brief and final, as the last of the black hole's mass converts to radiation, and the black hole simply ceases to exist. The time it takes for a black hole of stellar mass to evaporate through Hawking radiation is approximately 10 to the power of 67 years. A supermassive black hole, like the one at the center of the Milky Way, would take approximately 10 to the power of 83 years. And the very largest black holes ever likely to exist, the ones that formed from the mergers of many supermassive black holes over the course of the universe's stellar era, might take as long as 10 to the power of 100 years, or beyond. These are not numbers, not in any sense that the human mind can hold. They are placeholders for an immensity of time that no clock could measure and no mind could endure. But they are finite. That is the key. Every black hole will eventually evaporate. Every last remnant of every star that ever burned. Every galaxy that ever wheeled across the dark. Every planet that ever harbored water or warmth, or the improbable complexity we call life, will eventually dissolve into the thinnest possible whisper of radiation, spreading outward through a universe that is itself nearly infinite in extent and nearly zero in temperature. And then comes what the physicists call the heat death. Not a violent death, not a catastrophe, not an explosion or a collision, just an equilibrium. Just a final, absolute, unbreakable stillness. The universe reaches a state in which entropy is at its theoretical maximum. There are no more temperature differences to drive any process. There is no hot place and no cold place. Everything is the same infinitesimally small temperature. There is no more usable energy. No work can be done. No thought can be thought. No atom can fall into a lower energy state, because all atoms that still exist, if any do, are already in their lowest possible energy state. Time, as a meaningful concept, becomes questionable. What does it mean for time to pass in a universe where nothing changes? Where nothing can change? The heat death is not darkness. It is light, but light so thin and so cold and so uniformly distributed that it is, for all practical purposes, indistinguishable from nothing. It is a faint haze of photons with wavelengths so long they can barely be said to exist in any meaningful sense, spread through a space so vast and so empty that the chance of two such photons ever meeting is essentially zero. There is no sound. There is no complexity. There is no order of any kind remaining to perceive anything or feel anything or name anything. This is the end. This is how the universe dies. Not in fire. Not in ice, exactly. In something quieter than either. In in an infinite, patient, irreversible evening. And now I want to stay here with you for a moment, in the quiet, in the face of this image, because I think there are at least two very different ways to hold it. One way is terror, to feel the cold of it, to feel the loss. 14 billion years of stars, of worlds, of water running over stone, of creatures looking up at the night sky with something like wonder, of love and grief and music and mathematics, of children and of the memories of children, all of it flowing into silence, all of it dissolving, all of it in the end as if it had never been. This is not an irrational response. It is, in some ways, the most honest response. The universe does not preserve what it creates. Entropy is real. The arrow of time points in one direction. To feel the sadness of this is not weakness. It is a kind of love. But there is another way to hold it, and it is at least as honest and in some ways more useful in the night hours when sleep will not come. Everything that exists because the universe is not yet in equilibrium. You exist because the sun is hotter than the space around it, and that temperature difference drives every process on Earth, every photon of sunlight that has ever driven the chemistry of life, every breath of oxygen made by every plant that ever grew, every calorie of food that has ever become the electricity of your thinking. You exist because entropy is not yet maximum. You exist in the gap between order and disorder, in the fertile tension between them. The fact that the universe will one day reach equilibrium does not make that gap less real. It makes it more precious. The physicist Brian Greene has written about this with great care. The universe began in a state of extraordinarily low entropy, and it has been sliding toward higher entropy ever since. But the path from low to high is not a cliff. It is a long and winding road. And along that road, in the landscape between beginning and end, extraordinary structures arise. Galaxies, stars, planets, storms, rivers, cells, nervous systems, music, you. All of these are entropy's children, not its victims. They are the shapes that matter takes as it makes its slow way from order to disorder. They are the interesting part of the story. They are, in fact, the only part. Here is something that the mathematics of quantum mechanics tells us, and it is both strange and strangely comforting. In a universe of finite volume and finite number of possible quantum states, the recurrence theorem of Ludwig Boltzmann suggests that any configuration of matter that has ever existed will, given sufficient time, recur. Not because of any mystical reason, simply because of probability. If you shuffle a finite deck of cards for long enough, you will eventually deal the same hand twice. The timescales involved in cosmic recurrence are so vast they make the evaporation time of black holes look brief, a number written as 1 followed by 10 to the power of 123 zeros, approximately. But the math does not require us to take this literally. It requires us only to see that the universe is not linear. It is not a story with a beginning, middle, and end in the ordinary sense. It is a space of possibilities, and possibility, by its nature, cannot be exhausted, not even by heat death, not even by eternal expansion, not entirely. The atoms in your body were forged in the cores of stars that died before our sun was born. You are not made of something new. You are made of the oldest material in the universe, rearranged with extraordinary, temporary, improbable care into something that can sit in the dark and wonder about its own ending. That is not nothing. That is, depending on how you look at it, very nearly everything. I want to ask you something, and I want you to really sit with it before you answer. Somewhere in the long, slow trajectory from the Big Bang to the heat death of the universe, your life is happening. Right now. These minutes. This breath. This particular arrangement of atoms that can feel loneliness and hope, and the strange solace of staring into immensity. If you could send a single message forward in time to whatever comes after, a message that would endure somehow beyond the dissolution of matter, beyond the evaporation of the last black hole, beyond even the faint heat-death whisper of the last photon, what would you say? What do you most want the universe to remember about you? Write it in the comments. I am genuinely asking, and I will read every word.